In this video, we're in the multiple linear regression setting, and we're going to look at some of the consequences of under and overfitting a model. And what that means is either not having enough predictor variables in the model or having too many predictor variables in the model compared to the true model. So first, let's look at underfitting a model. And what that means is the true model has, lots of predictor variables, but our candidate model only has a subset of the true predictor variables. So basically it's not enough regressors are being used. So the column space of our candidate model is a subset of the column space of the true regression design matrix. So one of the consequences is that the mean square error is biased. So if we look at its expected value, which notationally we just call S squared, which is the sum of squares residual n minus k plus 1, this is a biased estimate. And it's actually biased upwards. It's larger than what it really should be. So that's one of the consequences of underfitting a model. And this upward bias makes our confidence intervals wider. It makes the hypothesis tests tend to be not as significant. So that's one of the consequences of underfitting. Another consequence of underfitting is that the least squares estimators are biased. So if we look at the expected value of beta 1 hat, we would hope that it's just beta 1, an estimate of the true regression parameters, but it's not. It's this, where A is this matrix here. Now A is, we call it A because this is often called an alias matrix. Now also we're going to prove these, and now let's look at overfitting on the last 2 pages we are. Overfitting a model, and what that means is we have a certain number of predictor variables used to predict Y. So this is like the true case, but for some reason we've overfit, or we have more regression variables than needed than the true. Okay, now this notationally can be thought of as this, where beta star, and that's a vector symbol, is 2 components, beta 1 and beta 2. So that way when you do that multiplication back, you get here. Now notationally, this design matrix we're just going to call X, beta star, and then the error term. So overfitting a model is, like I said, is too many regressors are being used. So the column space of the true design matrix is a subset of our column space of our candidate model, or our candidate design matrix. And so two properties that on overfitting are these. One is if the true model has k regressors, or k plus 1 beta parameters, and the candidate model, we just add one more regressor to the model and try to fit it. So we're overfitting the model. And then it has k plus 2 regression parameters. But each of these are corresponding to each other. So beta 1 and beta 1 star actually correspond to the same predictor variable, say x1. And this is the same all the way to beta k star, deals with the kth predictor variable. And then since we're overfitting the model, beta k plus 1 star doesn't have a corresponding beta in this model. So if we only look at the k plus 1 beta parameters, since we can't compare this to anything in the true model, we're only going to look at the corresponding ones, then the variance associated with the overfit model, the variance of the least squares estimates of the overfit model, are always greater than or equal to the variance of the true model beta parameters. And this is true for I equals 0 to k. And that's kind of a satisfying result. The second property in overfitting is this. We want to look at the prediction and what it does. So and to make a prediction, we need an x value. So we're going to call that x naught star, or x0 star. And so this is it. Remember, the 1 corresponds to the beta 0 parameter. And then we have k predictors, from the true model. And then we have k plus 1th predictor, where we've overfit the model. Now, if these first K predictors with the 1 go into a row vector, and then this one data point, so it's a scalar, goes here. So this point makes up this, and then we're going to just call it x0, and that's the row vector, and actually in the design matrix. And then this is a data point. It's x, k plus 1, 0. And the 0 means it's part of this data point, but it's a point. It's not a vector. So the predicted value using the true regression model here, remember this x0 is just this, which uses the k regressors, times our least squares estimate. That gets us a predicted value. In scalar notation, it's this. And now the overfit model is the same, so we use the same x values, but we have an extra predictor. We get a fit, another fit. Well, the variance associated with the fit of the true model is always less than or equal to the variance associated with the overfit model. Okay, and now we want to prove those. So the next 2 pages are proofs. So the proof of 1, that where we underfit our regression model, and then that the estimate of the error variance is biased upwards. I'm going to point you to previous video 38 and previous video 45 in this playlist, because I think the video is going to be too long if I prove everything. And we proved it in those videos. Now the proof that beta 1 hat is not unbiased is this. So the least squares estimate we've shown is x1 transpose, x1 inverse, x1 transpose, y. That's the least squares estimate. So the expected value goes into the y. But the expected value y is actually the true mean, which is based on this. Since we underfit, that it sort of expanded. So now let's multiply this into each of those. And this first part, those are inverses of each other, so we get the identity matrix. And then that times this, we get this. And this is the alias matrix. Oh, here's a point. Actually, I didn't plan on talking about this, but this is so worth knowing. So in this setting, we've underfit a model, right? We haven't used enough of the predictor variables. But let's assume the predictor variables that we missed provide 100% unique information, meaning they're orthogonal to all these predictor variables. Okay? Then the least squares estimate of this underfit model is actually unbiased, and I'll show you that. Now, generally, you can't do that. There is some sort of correlation between this predictor and some of the others. But if it's the ideal case and they're 100% orthogonal or providing unique information, then this product is 0, right? They're orthogonal, so the dot product or the vector multiplication is 0, and then it does provide an unbiased estimate of the true beta 1 parameter. And actually that kind of goes along to the power of what orthogonal predictor variables bring to a model. Even if you underfit it, you're still getting unbiased estimates of the true regression parameter. All right, but I digressed. So property 2 is when we overfit a model. So we're adding too many regressor variables. And then we looked at the variances associated with the least squares estimates of the beta parameter. So beta I hat, beta I star hat. And we need some notation here. And so this EI is going to be a vector with a 1 in the ith component and zeros elsewhere, right? But the star corresponds to the overfit model. So there's one more spot. And so the EI star corresponds with, it's a 1 in the ith component and zeros elsewhere, from 0 to k. And then this one, so this one we're going to use in the true model, and we have to use this one in the overfit model because there's an extra spot. And it's always 0 because it deals with the k plus 1 beta star hat, variable, which we can't compare with the true model. All right, so the design matrix is this. This is the true predictor variables. Actually, the first column is all 1s corresponding to beta 0. and this is the extra regressor or predictor variable. So now we have an overfit model. And if we look at beta I hat, we can pre-multiply it by EI, and then that picks off that ith beta. And here we have to use the star, EI star, and then this picks off the corresponding ith beta I star hat parameter. And so the variance of beta I hat is this vector product, and then the products can be taken out. The variance of beta 1 hat is actually sigma naught squared x1 transpose x1 inverse, so that's this. And we're going to leave it at that. Now let's look at the variance of beta I star hat. And then you can do the same thing, and then the EI vector comes, EI star vector comes out, and this is the variance of the design matrix, you know, transpose X inverse, and that's it. But we need to look at this one in more detail. Here we're going to leave it alone. Let's look at the, so now this EI vectors, like we said, is this, it's the expanded form. The design matrix has that extra column in it, and then you transpose it, it's this, that's the inverse, and that's the EI. Now, when we multiply this out, we get this 2 by 2 matrix. Remember, it's still inversed. And so what happens next, I'm gonna make reference to a video I have called the inverse of a partition matrix, where we do this generically. But I'm gonna cheat a little bit, because afterwards, when we multiply this vector in, and then this vector, these components actually go to 0, so they're not needed. So I'm only gonna list this component of this inverse matrix, okay, which is this, okay. So the inverse matrix is 2 by 2, so 1, 2, and then 1, 2, so it's 2 by 2. So this is the result, but I only provided this because this multiplication, those go to 0 anyway. So now when we multiply these in, basically we get EI, you know, in this, and then those EIs are multiplied by this, right? And then the sigma naught squared goes into both of those. That's what this piece is. Now we start doing things with it. So here, this part, so this is, well, we'll come back to that. So notice here, if you look at this first part, putting the E in there, that's actually the same as this if we were to transpose it. So if we take this and put a transpose around it, then we have to reverse them all, and it ends up looking like this. Now this one, from here to here, we left factor out an x k plus 1 transpose, and then we right factor out, and that's why we get this. And this result, you're just going to have to refer back to that inverse of a partition matrix. Here, this is the hat matrix for the true regression parameter, or true, you know, true model. It's a hat matrix for the true model. Now, this here, that's a 1 by k plus 1, and this is a k plus 1 by 1. So this is actually 1 by 1. It's a constant. And this is a constant. So it's a constant squared. And this is the perpendicular projection matrix onto the column space of x1. But x1, or x k plus 1, is not in that column space. So this is actually positive. And I minus h is a perpendicular projection matrix. It's idempotent. And it's always positive semi-definite, but because this is not in the column space of x1, then it's positive. So this result is always positive. Okay, and then I provide some additional insights. This is positive. This number, when it's squared, is positive. This is positive, and it's because it's a perpendicular projection matrix on the orthogonal complement, but that extra regression variable is not a part of this column space, so it's positive. So that implies when when we add this to the other side, we get this. So the regression parameters for the overfit model are always bigger than the true parameters. Now, part 2 of number 2 in an overfit model is the prediction. The variance of the prediction is more in the overfit model than the true model. And so the prediction is this, and now really it's a function of the data point that we used. That's the true prediction. So we're the variance of this, and it's, at a given point, or x naught. And so to find the predicted value, you use a data point and take it times the least squares estimate. And remember, this is a row in the design matrix, so that's a row matrix. So the variance of this, you take out the x naught and you take it out back transpose, and this is the variance of this. But the variance of the least squares estimate is this, sigma naught squared times this x1 transpose x1 inverse, right? So this is the variance. And we're going to leave that alone. We're not going to simplify it because we won't need to, ultimately. So now the variance of the prediction in the overfit model. Remember, this x naught has the same exact values here, except for it has one more regression variable. It's this variance, the x comes out. Remember, that's a row vector, comes out like this. And x is the overfit model with that extra regression parameter. So let's look at this in a little more detail. So x naught star is this, and the transpose is this. And x, remember, it has that, it's the true design matrix plus that extra regressor. And this is the transpose of it. Oh, I forgot the transpose there. So then we need to take the inverse of this, okay? So we're going to do this generically. Remember, and I'm going to have to push you off to the video I put out, inverse for partition matrix. So this, the result is going to be another 2x2 matrix, okay? So these are, it would be too long for my paper, so I'm not going to do it just yet. So the result of that inverse is this. So now when we multiply this together, I just did the left side first, right? So that times the first column, and then that times the second column, we get this. Now when we multiply this together, we get this result. Now we fill in all that stuff, and I skip a step because if you've made it this far, you're probably able to complete those steps. So A is actually, we already did it. It looks identical to the previous, property 1, where A was essentially this and this and this, and then the x0, was out front, and then this became a point, so that x0 is this one. But it ended up being scalar, so we could square it. This right here, these are scalar. These are 1x1 results. So if you transpose one, you get the other, right? That's xk plus 1 naught, xk plus 1 naught. So anyway, that's what, and you get 2 of them, and then you get this, filling in the results of that inverse matrix. And this is a 1x1, and it just comes this. So that D actually is there's an inverse associated with it, but it's scalar, so we can take it down. And then these are just number, and that's a number, so it's a number squared. So now, so this is a number squared, and this number is here, and this number is here, and that's squared, and we got 2 of them. So that's actually a quadratic, and then we keep the denominator the same, right? So this piece comes down. And then the numerator here is actually squared. So it's this number minus this number squared, and we get this back, and the denominator stays the same. Well, now, so that's the variance of the overfitted model. So now let's look at the difference here. And this actually is this piece right here. So this is the variance of this. But then we're subtracting off this piece, so we're left with this right here. Well, that's greater than 0. So this right here is the same quadratic form we had in the first example, where this is positive, and this is just a number squared, so it's positive. The variance is positive, so it's greater than or equal to 0. So if you subtract that to the other side, you get this. So the variance of the overfit model, the variance of a fit estimate of the overfitted model is always greater than or equal to the variance of the fit of the true model. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.